Hi, my name is Sydney, and this is my Lab 2 analysis. So in this lab, we analyzed the projectile motion of a real object. The goal of this was to determine how well mechanics can predict the real-world path of a moving object, and to compare two different computational models, one that assumes only gravity as the force, and the other that includes both gravity and drag. And so we collected experimental data and simulated the motion in VPython to be able to kind of directly compare prediction versus reality. Yeah, the main purpose of this was to test whether Newton's second law could accurately describe projectile motion under different modeling assumptions. So this is also known as the momentum principle, and it states that the net force of an object is equal to the mass times the acceleration, and we can show that in the VPython code with those two codes, and so that's how we can update the velocity and position of the object in the code. And then for net force, when we are only accounting for gravity, the only force acting on it is the force of gravity, which would be gravity times negative gravity times the mass, and it's just a constant downward acceleration, and gravity is 9.8. And we can show that in the code by setting b equal to 0. But when we're accounting for the drag force, we used the quadratic drag equation, and we just set b to a constant value, which I set it to 0.0017, and then we used this equation that multiplied the magnitude of the velocity times that constant squared, and then multiplied that by the normal vector of velocity, and then we showed that in the code there, and then F net would then become the drag force plus the force of gravity. So our experimental setup, we threw an eraser across the room. We set a 1 meter stick against the wall in the back to be able to measure the position over time in tracker. The camera was all stationary, and then I set the axis in tracker so that the initial position was when x was about 0, and then we set the y-axis so that it would be the bottom of the meter stick would be at y equals 0. And from that, with our mass being 0.0219 kilograms, we threw an eraser. The initial position ended up being a little bit off from 0, but it ended up being 0.059, and then the initial y position was 0.402 meters, and then the initial velocity was 1.466, and then the y component was 2.199, and then each time step was 30 frames per second, and so that was 0.033. And by putting that into the code, we made delta t be 0.033, and then we inserted the mass of the object as well as those initial positions and velocity, so that when we went in and updated it with that momentum principle and velocity update and position update equations, we were able to kind of update that and model that. In the end, the exposition showed that all of them were pretty similar, but with no drag, you can see that it is pretty much completely just a straight line up. There's really no deviation in that, and that's because it's pretty constant throughout the entire time, since the only force acting on it is the same force the whole time. And then our actual one was this blue line, and then that red line, because drag is accounting for it, you can see it starts pretty similar to when there's no gravity, or when it's only gravity, and then it kind of differs as it gets farther along, being less than when there's no drag, and that's because there's an extra force acting on it. And then our y coordinates, and so how high how fast the object got up and how fast it fell down, that we can see here. The no drag is this yellow line again, and then just like it was with the x component, the drag was much less than when there's no drag, because there's two forces acting on it. The actual y that we got from tracker was a little bit different, but that could have been due to a lot of different sources of deviation within the model and within using tracker. So some of the reasons for this deviation could have been, one, because the eraser could have been spinning, which would cause the Magnus effect, which basically is like a lift force which can alter the trajectory. Second, the eraser likely tumbled, changing its shape relative to airflow, which can cause drag to fluctuate over time instead of being constant. Another reason could have been how it was thrown. If there was a significant force when it was thrown, it could alter how that initial angle was. And then finally, there could have been human error in the tracker analysis, and so there could be measurement noise due to motion blur or click inaccuracy, and so there's a lot of things that could have caused kind of this change, but overall it still kind of shows that same that trajectory with no drag is going to be more than when there is drag. So the first question about terminal velocity. So terminal velocity occurs when the net force on a falling object becomes 0, meaning that the drag force and gravity balance out and the object stops accelerating. So in that situation, velocity would become constant even though the object would still be moving. So when we've looked at the vertical velocity versus time graphs from both computational models, in the gravity-only model, the velocity increased continuously, so it never reached terminal velocity. And then in the gravity and drag model, the velocity curve does start to flatten slightly, but it does not become perfectly horizontal, which means that this terminal velocity is not reached in the experiment. So the reason this is happening is because it was only the object was only in the air for a short time, so drag didn't have enough time to balance out gravity. And so if we wanted to actually measure terminal velocity, I would probably redesign the experiment by dropping the same object from a much higher height, like a stairwell or a balcony, and then track only the downward fall. In that case, velocity versus time graph would probably level off and reveal that terminal speed. And then if we were to imagine the object were initially thrown straight up, if we threw the same object straight up with the same initial speed as in my experiment, the total time before it returned to the ground would be longer than in my original angled throw, because without drag, projectile motion is symmetric, so time going up equals time going down. And then if drag was included, the object would slow down more quickly on the way up and fall at terminal velocity on the way down, making the total time even longer than the ideal prediction. So overall, throwing it straight up keeps it in the air longer than throwing it at an angle.